continuing with section 15.2, and in the first video we discussed how to find the limits when a function was elementary and within its domain. Then in second video we discussed how to show that an indeterminate form does not have a limit by choosing two paths that gives two different limit values. And then we said the only way you can show that a limit exists is if it's exists on all paths and they are the same. At least this is frustrating, but let me tell you, more than frustrating, because we're all mortals. We don't have infinite times to check infinitely many paths. So basically it's not possible. So we have to find other methods of showing that an indeterminate form has a limit. There is at least one very powerful trick that's converting a limit to polar coordinates, and another powerful trick that you will learn in your recitation, and you do problems on that. So how does this work? Instead of x, you plug in r cosine theta, and instead of y, you plug in r sine theta. As r approaches 0 from positive side, basically you use another calculus 1 tool or a single variable method tool in limits, because and you find the limit. How? Because what you're trying to do is basically in all of these conversions, you're trying to get rid of theta and basically make sure that theta is not affecting the limit, and that helps you just to convert to a one variable limit. Most of these things have squeeze theorem attached to them. Even if it doesn't mention it, you're really using the squeeze theorem. And there are other methods that are used that are calculus 1 methods, but a lot of them use squeeze theorem. Even if you feel like it's logical, the logic comes from squeeze theorem. And I'll tell you about that a little bit later. So let's do an example. Example 6, let j of x and y be e to the power x squared plus y squared minus 1 over x squared plus y squared. Evaluate the limit of g of x and y as x and y approaches 0, 0. So start from very beginning. If I plug in 0 and 0 for both variables, I get 1 minus 1 over 0, which is form 0 over 0. And there was a concern alongside when form 0 over 0 didn't have a limit. And we usually dealt with polynomials, and we were wondering if it had something to do with the degree of the numerator or degree of the denominator, and so on and so forth. Here is one of those cases, and I'm not 100% sure, but I see the degree of numerator is sort of e to the power, and so it's different from a polynomial. And how does this work basically? So to make this work, let's try to start with our good trick. Is our good trick going to work? Let's see, j of r cosine theta and r sine theta is going to be equal to e to the power r squared cosine theta plus r squared sine theta, which is going to be just r squared, minus 1 over r squared. Okay, theta just went away. So this is a good candidate to actually use the trick for. Now, Now that I have that, let's find limit as r approaches 0 from the right side of e to the power r squared minus 1 over x squared r squared. Sorry. From calculus of one variable, can I solve this? Let's see. Is this 0 over 0? Yes, it's 0 over 0. Form 0 over 0. And so if you remember, for calculus of one variables, when we were dealing with exponential and polynomials, exponential on top and polynomials on the bottom, a lot of times it was we actually were recommended to do L'Hopital rule. So let's do L'Hopital. What is L'Hopital? R goes to 0, and derivative of top, which is going to be e to the r squared times 2r e to the power r squared divided by 2r. And so the 2r simplify, and you end up with limit of e to the power r squared as r approaches 0, which is equal to 1. And so the limit is going to be 1. So this time around, we just used basically the conversion, completely got rid of theta for us. And we used a method that we learned in calculus of single variables. Let's see what else is there out there for us. Let's evaluate h of x and y, where h of x and y, and let's evaluate limits of h of x and y as x and y approaches 0, 0, and where h of x and y is equal to x squared over x squared times y over x squared plus y squared. So how do we do this? Looking at this, first of all, I see that these two have the same exponents. So each terms in the denominator has the same exponent, and there's only one term in the numerator that has the same the exponent adds up to 3, exponents add up to 3, and the denominator, each term has exponent add up to 2. This is a good candidate for the limits to exist. Why? Because the 0 on top is more powerful than 0 in the bottom. That's the thing. And so basically the lowest degree in the bottom is less than the highest degree on top, and so it makes it a good candidate. And so let's example 7. Let h of x and y be x squared y over x squared plus y squared. Evaluate limit as x and y approaches 0 and 0 of h of x and y. So far what we've done finding has been that we decided that if the so we decided that this limit actually may exist. So let's try to use our trick. So h of r cosine x, cosine theta, and r sine theta is equal to r squared cosine squared theta and r sine theta, which makes it r to the 3 over r squared. And if r is not equal to 0, which because we're in the limit, when it's just we're not at the point r equal to 0, this is true, it's going to end up with being r cosine squared theta and sine theta. Oh no, we didn't get rid of theta. Is there any way to deal with this? It turns out there is, because we know that cosine squared theta and sine of theta, they're both bounded. Basically, this statement is between -1 and 1, and with r being positive, cosine squared theta sine theta is between -1 and 1y, because cosine squared theta is between 0 and 1, and then sine of theta is between -1 and 1, and so when you multiply them together, the biggest they can get is 1, the smallest they can get is -1, and that's it. And so if I multiply all of these by an r, then this function h of r cosine theta r sine theta is squeezed between function -r and r. Is that good news? Yes, it is, because according to squeeze theorem, limit of r is 0, limit of -r is 0, and this one is squeezed between them, then this limit has to be 0. So basically we're using the information that we got from calculus of single variable, and this has to be 0 because this limit is 0, limit of r as r approaches 0 is 0, limit of -r as r approaches 0 is 0, therefore the limit in between is 0. So again, we clean it up, we write the limit, we plug in the r cosine theta, r sine theta for x and y, we clean up the function, we end up here. Again, theta should not matter in the calculation because theta just is all over the place, and the only way that we can do that is using squeeze theorem because of the information that we have about sine and cosine theta, and then being bounded and multiplying by a 0 by squeeze theorem makes it equal to 0. So it basically this is a consequence of squeeze theorem, that if you have a bounded set like cosine squared theta and sine of theta, and you multiply it by bounded function, that's this one's bounded between -1 and 1, and you multiply it by a function that is going to 0 at some point, then you end up with basically the entire product being the limit of entire product going to 0, and you see this is sort of a proof of it, as we showed before. Can we, so the example 8 is addressing. So some people may ask, okay, so you have a powerful tool, and that is plugging in r cosine theta and r sine theta. Can you use that to show that the limit doesn't exist? So example 8 is doing that for us. So let's say k of x and y equal to x squared minus y squared over x squared plus y squared. Evaluate the limits of k of x and y as x and y approaches 0, 0. And in this case, if I plug in k of r cosine theta and r sine theta, this is going to be r squared cosine squared theta minus r squared sine squared theta over r squared. So the r squared from top, r squared from bottom, they simplify, and you end up with cosine squared theta minus sine squared theta. And this is, if you remember your trig identities, this is going to be equal to cosine of 2 theta. Theta can be going on between 0 to 2 pi, and cosine of 2 theta can be any value. So basically the limit of k, this limit depends on which direction you're coming in, and gives you different values at each direction. So the limit does not exist, and so I couldn't get rid of theta. I couldn't do the squeeze theorem, and so that's what I ended up with. And even though this function was bounded because there wasn't any squeeze theorem, not multiplied by 0, it didn't work. So how do we phrase this? We phrase it as this limit depends on theta, which just says that if the limit depends on which direction you're coming to it. Limit does not exist. So let's do iClicker question 15.2. Evaluate the limit if it exists. And the limit is, the function is 6x to the third y over x to the fourth plus y to the fourth. Oh, so take a little break and try to solve it. So this is one of those situations that I'm looking at. The degree of the denominator is 4, degree of the numerator is 4. So each term in the denominator, degree of each term in the denominator is 4, degree of the numerator 3 plus 1 is 4. And that kind of brings me up to the point that this cannot have a limit, because it's a form 0 by 0, 0 over 0, by the way, I haven't talked about that. Form 0 over 0, and it just seems like that it shouldn't exist. If I plug in r cosine, let's see, if I plug in limit as r approaches 0, theta goes, I don't know, and then plug in r cosine theta, r sine theta, I get 6r to the 4 cosine to power 2 of theta times sine of theta divided by r to the power 4 cosine to power 4 theta plus sine to power 4 theta. Oh, this is not going to be looking good. And so one thing is that I see that the r to the power 4 disappears, and I will be depending on sine and cosine, and so that's the theta does not disappear. But then you have to show that it actually after simplification theta doesn't disappear, or you have to make some sort of an argument about that. Basically, simplify it all you can and say theta doesn't disappear. So that's one way. Not the best way, because again, sometimes you don't know after you simplify if theta can disappear or not. Right? This one requires a lot of trig identities and so on and so forth. Now, is there any other way of doing this? Yeah, one way is to do this along the path x equal to 0, and so the limit is going to be limit as y approaches 0. Put in 0 for x, you get 0 over y to the fourth, and that is 0. And then other way is limit y equal to s along the path y equal to x, and this is limit as x approaches 0 of 6 x to the power 4 divided by 2 x to the power 4, which is going to be 3. So these two are not equal, so the limit does not exist. So again, I did a cyan color to show you that sine and cosine don't go away, but you have to make sure you know your identities to say that they don't go away. Basically, that theta doesn't go away. This makes it simpler than that. And that is just finding two paths that give you different value for the limit. Okay, another I click here question 15.2D, evaluate the limit if it exists of limits as x and y approach 0 and 0 of 6x to the third y squared over x squared plus y squared to power 2. And so take a moment and solve and come back. So this time I see that then the degree of the numerator is going to be 5 and each term in the denominator. So what are the terms in the denominator? X squared plus 2xy, x to the fourth plus 2x squared y squared plus y to the fourth, right? If I expand this, I get x to the fourth plus 2 times the first one times the second one, and plus y to the fourth. The degree in the denominator is just nicely is 4 for each term, and so this is a candidate for the limit to exist. So let's write it, write the trick, see if the trick works. Again, there are other tricks and you will learn at least one in your lab. And so you get 6 r to the power, this is r to the 3 cosine to the 3, and then r to the 2 cosine to power 2 sine to power 2. So cosine to the power 3 theta sine to power 3 theta over x squared plus y squared is just r squared, so r to the power 4. So what you're left with is 6r cosine to the power 3 of theta and sine to power 2. I'm sorry, this one should be 2 to power 2 theta. Okay, so my question is this thing bounded? Yes, it's bounded. That's very essential. If you can simplify it, use another trick. This one is simplified already, and I see it's a bounded value. It's between -1 and 1. Therefore, by squeeze theorem, this is going to be equal to 0. And so the answer is B.